Hello, my name is Mohamad El-Batal. I am CTO of Systems at Seagate, and I part of the CTO office responsible for various initiatives, within systems as well as HDD. One of the solutions that we are going to talk about are the connectivity aspect of HDD storage and why it is important for us to look at the future with an open mind towards advancements in connectivity solutions for HDD. So, see, as we create more data, we're going to see a large adoption of HDD continuing to grow as we have, close to 400 zettabytes of data created in 2028. IDC data is showing that only 5% of that data will be stored. We're not going to be able to have the power or the space to actually store the 400 zettabyte of created data. So, there's the only way we're going to be able to get to store a little bit more than this is with our ability to have better sustainability, better capacity, growth within the same power form factor and within this same physical space. So, enterprise, cloud, or consumer are running into the same situation. Gen AI is going to exacerbate this situation where we're going to create a lot more data as Gen AI is creating its own data now and utilizing a lot more data for training. So, the vision of trying to create smarter AI doesn't come for free. We need the ability to grow the data set that it's learning from and feed that output into a semi-archival environment where HDDs will be utilized. So what is Seagate doing about this? The growth in the slope of the growth of capacity used to be trickled, 1 to 2 terabyte at a time. HAMR, as Praveen talked about, the next generation drives will expedite that growth curve and will have much larger step functions in terms of capacity. So that basically will drive additional growth in capacity, but what else we have to do to be able to utilize all this capacity at this point from an interface, not only the speed of the interface, but the flexibility and the modernization of that interface. Trying to replace HDD technology in the data center is not likely in the next decade or two, right? If we, to replace all the spinning media with rotational media, that means basically a huge investment will have to be put in, about $200 billion of additional investment from what's already being invested, as well as, the return on investment is not there for flash. Those guys who are printing more flash, they have to be aware of the return on investment from that perspective. So, the current prices are going up for a good reason. Somebody has to make money on that stuff. So what are we doing about it? So a few years back, in actually 2021 we started. 2022 we got the NVMe HDD specification released through OCP. It was work from Microsoft, WD, and Seagate. We collaborated on creating a specification that defines the ideal HDD that will work alongside of SSDs and provide solutions with leveraging the feature set that are created within NVMe to satisfy the modernization of the data center. We have 2 EDUs that got released and sampled, and EDUs are, again, they're not really product. They are, to be careful with that, is they're engineering development units. They're proof of concept that allow us to play around with the technology and see what the impact is. So far, we've sampled and we've got feedback, and we're going to continue to march towards that. So why are we doing it from sustainability perspective, today we have too many components in the JBOD. You know, if we look at, you know, what it would take to connect hard drives versus SSDs. SSDs tap into the processor PCI bus directly. Great. That really is efficient. HDDs need to do the same. You know, we have a bunch of chips that are burning power in the data center that shouldn't be burning power. They shouldn't be using some of the TCO equation that is causing us to, you know, expand more on the spending. So, you know, from that perspective, the need for shrinking the distance between the drive and the main CPU or DPU or GPU in the future is necessary. And the best way to do it is a combining of SSDs and HDDs through the same interface. The stack, from a, you know, Linux stack we're looking at here, simplification of the stack will help reduce errors, reduce problems, reduce proprietary firmware, and make an open environment. So ideally, cost reduction, simplification of the stack, those are the reason why we're doing it. And you know, the industry wants to do it tomorrow. The problem is transitioning technologies like that or interfaces to drive means infrastructure re-engineering. So we have to keep that in mind as we go through this. We did. We actually looked at, can we use the same backplane? Can we use the same connector? Can we use the same SoC on the drive to drive both NVMe and SATA in the transitional period? There's no need to create a bridge, right? So the idea that we actually came up with is to provide this, you know, we started with thinking about U.2, U.3, trying to match what connectors of SSDs, but in reality, we needed to match the connector of the HDD. The SATA connector is what's being deployed in the data center, and that's what we deployed. And we made sure that the connector guys worked out the SI signaling, and it actually works. So from that regard, the transition can happen if we leverage the same boxes, same backplanes, same connectors. What has to change is the interface. You know, instead of SAS IOCs and expanders, we need to connect PCI connectivity. Now, the other study that we had to go through within the specification is look at the signal integrity. Can we run PCI as long as we did with SAS? Well, we can actually do it. The channel model shows that we can do 25 inches minimum of trace with Gen 3. Gen 3 is fast enough for HDD. You know, that's a gigabyte per second per lane. So, you know, even in worst case efficiency is still more than 600 gigabyte per second. You can actually still do it. 600 megabyte per second is more than enough. So it's not only capable of doing it on the same backplane, it's more capable than SAS 3 in that case. So in summary, you know, if you really look at the amount of innovation we can create in here when we move an HDD rotational media to NVMe, it opens the doors for being able to better utilize features like multi-actuator that Praveen talked about. You know, today we have it in SAS and SATA, and they're being utilized, but it's kind of, you know, utilizing LUNs instead of ports was problematic for some of the RAID technology out there, but it worked out after a bunch of work. Now, NVMe namespaces we are used to having multiple namespaces on SSDs, so we can actually utilize multiple namespaces for rotational media. You know, optimizing the ability to do reman or retiring a head that failed from a drive and keeping it online, that can be done with ADR, adaptive drive regeneration. And it could be done with using namespace management or elastic capacity as a feature that could be added to, actually there's a TPAR that for elastic capacity that is still, I'm not sure if it's canceled or it's waiting, right? All right, it's been withdrawn. So we're going to use namespace management then. But the idea is that we have to come up with something, right? Yeah, so from that regard, it really is the next stage also talking about, attestation. HDDs haven't done attestation yet without, some studies that we've been doing on SAS attestation and SATA, but with NVMe, you could utilize the same, SPDM and MCTP over VDM or DOE to do the same thing. So, the idea of having NVMe or fabric connectivity to GPU direct, as we go in the AI world, the massive amount of data that needs to be used in training or in offloading into archival needs to be optimized with the capability of directly connecting to a GPU. Well, NVMe can actually do that with fabric GPU direct capability from Mellanox or from NVIDIA. So with that, host memory buffer is another idea that's being tossed around. And what can we offload from having to carry on the HDD? Can we reduce the cost of an HDD if we remove some of the NAND that's being utilized to store to store data for media information and head tuning, et cetera. So, that's another idea that we have some slides later on to talk about, but I'm not sure if we'll have time. Controller memory buffer is another one that's going to be enabling a reduction in needs for the RNIC to carry a lot of the DRAM in an NVMe or fabric solution. So you can actually have a small controller memory buffer on each drive. 8 megabyte is sufficient based on the performance aspects of an NVMe HDD. You still can handle a couple hundred IOPs in 8 megabyte from that regard. Then, we looked at ZNS as, for, SMR, host managed SMR or SMR. Basically, the ZNS functions were created with, based on the HDD utilization of SMR. So it can actually tie in directly and start being utilized for that. CDL, again, there was a TPAR that was withdrawn, but it delays in releasing NVMe. That doesn't mean that it's not going to happen. It really needs to happen and will happen, but we need to have the economy of scale that will drive us to simplify and reduce power and reduce this solution. Flexible data placement could help us even do a better job with regards to placing data on rotational media so we can read it faster. Same ideas as SSD, same leverage. eBPF is another one that could provide potential, computational storage, even if we have a small ARM processor laying around that we can actually make available for the host. So you got 100 million drives out there. They can do quite a bit of ARM processing. So a lot of these things, we thought about. Today, I'm not sure how much time I have left. I don't see the clock anymore. 4 minutes. I'll try to step through these real quick. Controller memory buffer, for those of you who are not familiar with it, is basically mapping some memory space within the SoC, the system on chip device that we have on the drive to allow for queues and data to be placed by the RNIC, by the NVMe or fabric controller directly on the drive. And we just pull the command queues directly and put the data back for the host to RDMA directly to the host. So that's one idea that basically today we have. This is kind of today's model of NVMe or fabric. It requires all these components, whereas SSDs, as you can see, they can actually pull directly from CPU memory. Next step that we actually are prototyping, are trying to do NVMe. We actually have prototype being built to do this next step, which is GPU direct with SSDs and HDDs directly behind a DPU. So the DPU will actually do the management of both of them together. And the next stage would be to eliminate some of the the switch needs, if you have enough lanes on the DPU, you can actually connect them directly, which will happen. And after that, just mainly, control memory buffer enablement and trying to reduce the number of chips and stacks between them. Host memory buffer, again, the problems we're solving there is like, the drives have cache and NVC, it's called non-volatile cache. As we want to, prepare to vault that cache, sometimes it takes rotational media energy to do it, so you have a very limited amount of cache. If you have a host memory buffer, well, you can do a lot better than that. You can actually vault it back to an RDMA back to the host and put it in a little bucket that the host will make available to us. Same thing with rotational media information. I'm sorry I'm going through this fast, but the slides will be there. They're ideas. They're not really something that's going to happen tomorrow, but those ideas will be seeds for the future. I think we want to continue to make improvements for this rotational media because it gives us capacity that is not available elsewhere for an online solution. So in summary, basically the faster slope of growth and capacity of hard drives is going to require us to put more, attention to, to the technology that we have and how we're going to access it. Enabling HDD with NVMe will save cost, will improve performance, and will reduce power. And we urge the community to work with us, whether at OCP or on the NVMe committee, to introduce some of these features and make them available. Again, be patient with us. It's going to happen, but it's going to take a little time because the scale of data centers has grown so big. We tried our best to keep it within compatibility regions of backplanes, et cetera, and the software is compatible. Now we're dealing with just making sure all the stack of silicon that needs to connect to it is ready and people are willing to spend the money for it. Thank you very much.